In this module, we're going to build up a picture of the climatological circulation of the atmosphere. And by that, I mean a long-term average where the weather systems and the storms have all been averaged out to leave a picture of just the main wind belts. So first, we need to talk a little bit about the atmosphere. So unlike the ocean, the atmosphere has no clearly defined upper boundary. It just slowly becomes space. So if we look at this graph here on the left, we've got altitude on the vertical axis in miles on this side, kilometers on this side, and on the bottom we have air pressure. And so here at sea level, got an air pressure, atmospheric pressure of 1,000 millibars, and then the red line shows how that changes with altitude. So at about 5.6 kilometers, we have 50% of the mass of the atmosphere is below you. So about 50% of the molecules in the atmosphere, the air molecules, are below you. By 16 kilometers, 90% of the mass of the atmosphere is below that level. Commercial aircraft fly at around 11 or 12 kilometers. As we keep going up, we start getting into this long exponential tail. So there is still some air above you if you're at 100 kilometers height above the surface of the Earth, but the vast majority is below you. So even if we consider that the atmosphere is 100 kilometers thick, it is still very thin compared to the radius of the Earth, or the diameter of the Earth. So if we look at this photo here of the International Space Station and the space shuttle, this blue haze here is the atmosphere. So very thin compared to the diameter of the Earth. So what's the atmosphere made up of? I'm going to start by considering dry air, and dry air is 78% nitrogen, 21% oxygen, and the remaining 1% is largely argon, and then there's other gases, including CO2, which is a little bit greater than 400 parts per million, but it's increasing all the time. So the reason that we consider this as dry air to start with is because water vapor is variable in terms of both time and space. So parts of the world like Antarctica are always very dry. Parts of the world like the tropics tend to be a lot wetter. On a rainy day, obviously there's a lot more water vapor in the atmosphere than on a very dry day. So this climatological atmospheric circulation, so remember the one with all the weather systems averaged out, has three driving factors. On a large scale has three driving factors. One is uneven solar heating, which we talked a bit about in module 4.1, pressure gradients, and Earth's rotation, which will be the subject of the next video. So in module 4.1, we saw this figure here on the left. Just to recap, so we had incoming solar radiation, the red line here. So it's more in the tropics than at the poles. So we have this curve here. The long wave radiation emitted from the Earth is this blue line here. So this was the radiation emitted because of the temperature of the Earth. So we have an area in the tropics where we have more incoming solar radiation than we have outgoing long wave radiation. So we have a surplus of heat and energy in the tropics and a deficit at the poles. So in order for the tropics not to continually warm up and the poles to just get colder and colder, we need to be able to transfer that heat from the area of surplus to the areas of deficit. So the atmosphere and the ocean both contribute to the transfer of this heat. About 2/3 of the transfer is done by the atmosphere and about 1/3 by the ocean. And as I said earlier, one of the big drivers of the atmospheric circulation is this differential heating. So there's three different ways that you can transfer heat. One is conduction, which is the direct transfer of heat. So this is what you would experience if you were holding on to the end of a metal rod that you stuck in the fire. and the heat will come down the metal rod just by molecules vibrating faster at the hot end, banging into ones, and they slowly move down, and the heat moves down the metal rod. A second way of transferring heat and energy is radiation. So we've seen that in context of solar radiation, transferring heat and energy from the sun. And the final way requires a fluid, so either a gas or a liquid, and it's known as convection. So this is when you have warm air or warm fluid rising and then running along the top of whatever it is, in this case a room, and then as it cools, it sinks and the cold air runs along the floor until it gets back to the heat source, and so we end up with what's known as a convection cell. So here we have an example of what would happen if the Earth only had this uneven solar heating. So it's not what happens. The picture when we include the Earth's rotation is more complex. So you'll notice that there is this convection cell set up where the air is rising in the tropics, where it's warmer, running along the top of the atmosphere and cooling at the poles, and then that cooler air runs back along the surface till it gets to the tropics and rises again. And that's generating this limb here that's near the surface where we have flows going from the poles to the tropics in this example. So what's causing those surface flows? Well, it all has to do with pressure gradients. So the pressure at sea level is just the weight of a column of air above that part of the Earth. So at sea level, you have 14.7 pounds per square inch of pressure on you. So cold air is more dense than warm air, and that's because cold air is heavier. The molecules don't vibrate as much, so they don't take up as much volume for the same weight of air. So we have a high pressure under the cold air and lower pressure under the warm air. So if you take a column of warm air here, it's all lighter, so it will be lighter than this column of cold air over here. So at ground level here, we have more weight of air on this side under the cold air and less under the warm air. But anywhere on one of these black lines, the weight of the air above it is the same. So to get the same weight of air at this point under the warm air, you have to take a larger column of air than you do for the cold air over here. So the air near the surface is going to want to travel from the area of high pressure to the area of low pressure. This is the same principle as when you have a sloping board and you have a marble on it. It's going to want to go from the high end of the board to the low end of the board. The shorter the distance between the high and the low, or the larger the magnitude difference between the high and the low, the greater the pressure gradient and the faster the flow. So going back to our marble on a board example, the steeper the board, the faster the marble will roll.